All righty. So here's where we are starting. Okay. So we're going to be talking about the graphs of f prime. Okay, so again, part of calculus, right, is being able to not only look at expressions and functions and stuff and work with those and be able to determine analytically what's going on and like intervals increasing, decreasing, relative max, relative mins, intervals of concavity, points of inflection. We want to be able to do that, okay, given the original function. But we also want to be able to look at like graphs and be able to interpret graphs and read information from those things too, and do the same thing, be able to find relative maximums, relative minimums, points of inflection, concavity, intervals increasing, decreasing, all that stuff. So our focus, we're going to shift focus now from f, the original function, and using f to then find the derivative f prime and then f prime prime, and then describing the original function. We're now going to start by being given the graph of f prime, and then using that graph to then talk about both f and also f prime prime to the second derivative. Okay, so we're kind of changing kind of like our focus or our point of observation, I guess, from the original function. Now we're going to be observing just the derivative and then using that to talk about different pieces of things. Okay, so before we do that though, we're going to jump right into like a quick definition review. Okay, so a function f is increasing when f prime of x is what? Positive, okay? Okay. And I'll add on an interval there. Okay. So, if we are given a graph of f of x, and we want to kind of like observe or see where f of x is increasing, what are we looking for? So if we want to figure out when f is increasing and we're given the graph of f of x, what's kind of like the thing or behavior we're looking for? Positive slopes of it? Okay. We can also just say something like the graph just goes up from left to right, right? I mean, this is like something that we've seen before, right? So positive slopes, or positive tangent slopes, I guess I'll say. Okay, or the graph goes up from left to right. Okay, I'm going to abbreviate left to right, which is an L arrow R like that. Okay, so you can talk about positive tangent slopes or the graph goes up from left to right. Right, some simple stuff like that. That's how we can tell if we're given f and we want to know when f is increasing. That's what we're looking for, right? Okay. If we're given the graph of f prime, what are we looking for to determine when f is increasing? Okay. So when it's greater than 0. Exactly right. So if the graph shown as f prime, the graph of f prime will be above 0. Or the x-axis, you could also say, right? Okay, or you could say, or it'll be positive, right? Okay. All right, so next thing, a function f of x is decreasing when f prime of x is negative on an interval, right? That's why we use that first derivative test. And use the first derivative to determine when a function is increasing or decreasing. Okay, so f is decreasing when f prime is negative, those negative slopes. Okay. If we are given the graph of f, what does decreasing look like? Yeah, negative tangent slopes, or the graph goes down from left to right, right? Okay. So that's what we're looking for, right? And again, that's stuff we've seen, that kind of behavior we've seen since probably Algebra 1, maybe even before Algebra 1, right? You're identifying where a function was increasing or decreasing and stuff like that. But now with the calculus, right, if the graph shown is f prime, what are we looking for? If we want to know when a function, when the original function is decreasing, and we're given the graph of f prime, what are we looking for to determine when the original function is decreasing? When f prime is what? Below 0 or below the x-axis. Okay, let me open that in parentheses. Okay. All right, next question asks, a function has a local maximum. Local maximum means the same thing as a relative maximum, so we can also use the word relative there. Okay. The idea for local is that, you know, in a neighborhood of points, it's the highest point, right? So your hill, right? Your hill there, but also relative to the other points around it, it is relatively the highest point, but it may not be the highest absolute point of the function. Okay. So a function f has a local maximum when f prime does what? Okay, f prime of x is 0, but not just that, right? Because if it's just 0, we can be equal to 0. Like we can have a critical point, and it's not necessarily a local relative maximum. Or we could have a critical point, and it's not necessarily a relative max, it might be a relative min, right? Because critical number doesn't necessarily mean it's got to be a relative max. So what are we really looking for? Changing from positive to negative. Exactly right. F prime changes from positive to negative. Okay. And of course, we also want to make sure we include the idea of continuous there too, I think. Do we? Actually, no, we don't. Never mind. Just forget that. Just that. Change from positive to negative. Just change from positive to negative. Yeah. Just change from positive to negative. Okay? All right. So, if we have the graph of f of x, well, how do we see a local or relative maximum? What does it look like? Okay, well, just in this case, not the hills and valleys, just what? Just a hill for this case, yes. Yep. Okay, so if the graph shown is f of x, a local, okay, or I'll put in parentheses, relative maximum looks like a hill. Okay. If the graph shown is f prime, though, what are we looking for there to then see where f has a relative maximum? The graph of f prime, okay, crosses the x-axis, and this might not be the most succinct way of putting it, the most elegant way of putting it, but so we're going to say the graph of f prime is going to cross the x-axis, okay, to the left of, or to the left, sorry, not to the left of, just to the left, f prime is positive. To the right, f prime is negative. Okay, so to identify that relative extrema, we want our, in the graph of f prime, okay, so to identify the relative maximum of f, given the graph of f prime, we want to see that it crosses, that f prime crosses the x-axis, so we have a 0 there indicating a critical point. To the left of that 0, we want f prime to be positive, indicating the original function is increasing. To the right of f prime, we want that derivative to be negative, okay? So that way the original function is decreasing, changing from increasing to decreasing indicates that relative maximum. Okay? And then, of course, with the local minimum, it's going to be the same thing. We're just going to switch around some of the signs and stuff, though, too. Okay, so a function f of x has a relative or local minimum when f prime of x is changing from what to what? Yep, the reverse, right? Changes from negative to positive. And basically, we're going to just swap words here, right? Swap the idea. So if the graph shown is f of x, a local or relative minimum looks like now a valley, as Mario said. Okay, or a trough is another word you use sometimes. Okay. And if the graph shown is f prime, well, we're going to do again a similar kind of thing here. Then the graph of f prime crosses the x-axis. Okay. To the left, f prime is negative. To the right, f prime is positive. Okay. So where our first derivative changes from negative to positive, the original function is changing from decreasing to increasing, indicating that relative minimum. Okay. All right, point of inflection. A function f has a point of inflection when f prime prime does what? From negative to positive or positive to negative, right? Points of inflection occur when we change concavity. So when f prime prime changes from negative to positive, I'm just going to put or vice versa. Okay, I think that is like a sufficient. I think you're allowed to use vice versa, I'm pretty sure. Okay. Okay. So how do we determine a point of inflection given the original function? What are we looking for? What happens at a point of inflection in the original function? What makes a point of inflection a point of inflection? What's changing there? Concavity, exactly right. So if the graph shown is f of x, the concavity will change. Again, from concave up to down, or vice versa. Okay? Bless you. Let's hold off on the next one here. So let's hold off on talking about f prime for right now. Let's just jump to f double prime because that's the more familiar one, right? So how do we use, what are we looking for in f prime prime? What have we used, how have we used f prime prime in the past to determine points of inflection, right? What do we do with that second derivative to determine points of inflection? So again, we're going to skip this next bullet right here. We'll jump down to the third bullet right here. How do we use the second derivative to determine points of inflection? It's when the second derivative is what? What? No. We first want to determine when the second derivative is 0 or crosses the x-axis. So the graph, right? What do we do to find a point of inflection? We set our second derivative equal to 0 or where it doesn't exist, right? And then we identify those possible points of inflection. So how do we set it equal to 0 in the graph? Well, where the graph of f prime prime crosses the x-axis. That's our zeros. Those are our zeros. And f prime prime changes from positive to negative or negative to positive at that point. Okay. That's what we do, right? Second derivative equal to 0, and see where the second derivative changes from positive to negative or negative to positive at that point. Okay, now, here's where it gets a little bit funky, and I was trying to explain this earlier, so we'll go through it again here, right? So if the second derivative here is changing from positive to negative, what's going to be true about the first derivative? Well, if the second derivative is negative, the first derivative will be, decreasing. And if the second derivative is positive, the first derivative will be increasing, okay? Because these two are related to each other, f prime and f double prime are related to each other in a similar way that f and f prime are related, right? Where f prime is positive, f is increasing. Where f prime is negative, f is decreasing. So, where f prime prime is positive, f prime will be increasing. Where f prime prime is negative, f prime will be decreasing. They're related to each other in the same sense that f and f prime are, f prime and f double prime. So if f double prime is changing from positive to negative, f prime will be changing from increasing to decreasing. And what happens when you change from increasing to decreasing? What is there at that point? A relative what? Maximum. Or the second derivative, we could have a point of inflection in the function where the second derivative changes from negative to positive. Well, if the second derivative is changing from negative to positive, the first derivative will be changing from decreasing to increasing. What kind of thing occurs where something is changing from negative to positive? Relative minimum. So in other words, the point of inflection, I'm going to abbreviate that here, POI, the point of inflection, POI, will be either a relative maximum or minimum. Okay? The point of inflection will be either a relative maximum or relative minimum. So the point of inflection of f shows up in the second derivative as a 0, and the second derivative changes from positive to negative or negative to positive at that point. But it also shows up in the first derivative as a relative maximum or minimum of that first derivative. Okay? All right. Let's finish these up here, and we'll move into some examples so we can actually see this in action rather than just having a bunch of words thrown at us. Okay? A function f is concave up when f prime prime is positive. Okay. If the graph shown is f of x, what does concave up look like? A cup. Okay. Remember that there is no bearing, all right? There's no like concave up can only happen for increasing or concave up can only happen for decreasing. We can have concave up increasing, it looks like this. We can have concave up decreasing, it looks like this. Okay? So concavity and increasing and decreasing, they are, not, they're not really related to each other. You can have both, any combination of both things. Okay? All right. If the graph shown is f prime, what's going to be true about the graph of f prime? If f prime prime is positive, f prime will be what? Increasing. Exactly right. Okay, and of course, if the graph shown is f prime prime, the graph will be above the x-axis, right? That's how we know it's positive. Okay. And then for concave down, pretty straightforward from here, right? A function is concave down when f prime prime of x is negative, right? Okay, if nothing else, we can just, use our opposites here to help us, right? If the graph shown is f of x, the shape of f will be a frown, much like many of you are doing right now because you don't like this new stuff. Okay, or maybe your brain is frowning right now. Okay, and again, you can concave down, decrease, or you can concave down, increase too, right? Either one is possible there, and that's what they look like. All right, and then if the graph shown as f prime of x, well, if f prime prime is negative, f prime will be what? The decreasing. Okay. And if the graph shown as f prime prime, we know it's concave down, then when f prime prime, the graph will be below the x-axis. Okay, that was fun. So let's take a look here at example 1, the graph of f of x. All right. So in this scenario, and I think these numbers are supposed to be like 1, 2, 3, 4, 5 here. We're just counting by ones, okay? So I know the numbers didn't really show up that well, but you can relabel if you really want to here. Okay. Example 1 just says label the graph of f of x. So let's do that. And let's start with intervals where this function's increasing, okay? So we're given f, and we want to label where f is increasing. So what's the interval for where f increases? Yeah, it looks like about -3.5 to what? About a half, right? About a half there. It's increasing throughout there. Okay, so I'm going to do this in a bit of a weird way here. I'm just going to like visualize this. So I'm going to put like if you want, you can put the interval there. So, you know, -3.5, comma 0.5 if you want there. Okay, is there anywhere else where it's increasing? 2 to 3. Okay. Is there anywhere else where it's increasing? Nope. Okay, good. Important to recognize that we need to stop at some point too. All right, how about decreasing? Are there any intervals where this function is decreasing? 1/2 to 2, right? Kind of like right in here. So, oops, I forgot to put the decreasing there. I'll just write it right there. Decreasing from 0.5 to 2. And then where else? Is it decreasing? 3 to 4.5, yeah. Okay, very good. Let's see here, we already did, so we did increasing, decreasing. Let's look at the relative maximums. Do we have any relative maximums? And if so, where? You got about 0.5 again, that peak right here. So right here, I'll put a point there. Okay, and I'll say that is a relative max. Relative maximum. I gotta be careful here. I don't want to abbreviate too much there. What other kind of maximum could we say that is? It's the absolute maximum too, right? It is the highest point of our graph. Okay. We could also call it a critical point too if we wanted to. It's where the derivative. Okay, can we name it? We could name it a critical point if we wanted to as well. Okay. So all those things are true about that point up there. Do we have any other relative maximums? Say what? That's a good question here. Let me think about that. I think we want to say that it is not a relative maximum there because the function is not continuous. I think we want to say the function is not continuous there, so it's not. What's that?
It looks like it's filled in.
The filled in dot. I see what you're saying, but from the what I guess what I'm trying to say is that from the function is not continuous at 3 because we have that jump discontinuity there. So I want to say there's not a relative maximum there, but I will check on that just to make sure. I'll get back to you on that, but I'm pretty sure that there is not a relative maximum there at 3. Okay, so really we just have the 1 there, the hill. Okay, so do we have any relative minimums? Do we have any relative minimums? At 2, right here. This is a relative minimum. Okay. It is also therefore a critical point. Okay. This is the kind of critical point though where the derivative would what? Would not exist here. Okay, because we're having like a sudden change in slopes. It's not a nice smooth transition like we had up here. So here the derivative would be 0. Here is an example where the derivative would not exist. Okay, thus creating critical point. Okay, do we have any other relative minimums in this graph? Do we have any more? Okay, so if we're, and we'll go ahead and put a point there at the end, and sure. And we'll say that that is the absolute minimum right here. But is it a relative minimum? No, it's not a relative minimum, just an absolute minimum. Okay, so here's an example of when you can have a relative extrema be also an absolute extrema. But in this case, this is just an absolute minimum, but it's not a relative extrema. Okay. Okay. Good. All right, so we talked about all that. That's all of our first derivative stuff. Now let's talk about all of our second derivative stuff. So for example, let's talk about the intervals of, actually let's talk about the intervals of concavity. All right, so do we have any intervals where our function here is concave up? And if so, where do we start being concave up here? What's our farthest left x value where we start being concave up? So is this concave up right here? No, that's concave down, right? Maybe we can start it that way. Where do we stop being concave down in this first interval here? At about -2, right? About -2. So I'll put that right here to the -2, and we'll say there, right from there to there, that's concave down, we'll say. And again, I'm going to abbreviate just because I don't have a whole lot of space there. And again, we'll say that's the interval from what? -4.5 to -2, we'll say. Okay, so I'll put that down there. Okay. All right, and then at -2, we start changing to concave up right there, right? And then about where do we stop being concave up, though? I think before 0. It looks like we were concave down a little bit before 0. So I'd say about -1 maybe, right? It looked like we were concave up, and then it starts to curve back around the other direction there. So I'd say maybe like -2 to -1 or so. We're concave up. Okay. Since we changed from concave down to concave up, what have we located? Point of inflection at -2, right? Because that's where we changed from concave down to concave up. So at -2, point of inflection. And again, I'm going to abbreviate just because, Okay, I'm just going to abbreviate there because we just don't have a whole lot of space. Okay, now, this is also a critical point. Okay, it just kind of happens to be that way. Right? I would say it's a critical point there. It looks like the derivative at that instant would be 0. Okay, it looks like the derivative at that instant would be 0. So we could also call it a critical point. All right. All right, so we're concave up to about -1, and then we changed back to concave down. And then how far are we concave down? Where do we stop being concave down here? at like looks like 2, right? From -1, we start being concave down, concave down, concave down, concave down to 2. So up to 2, we are now concave down again. I guess I can write the whole way out here. And that's from -1 to 2. So where's another point of inflection? At about -1, it looks like. Okay, point of inflection there. Okay. What does it look like? What does it look like the concavity is from 2 to 3? I'd say concave up. Which means, what happens at 2? It's a point of inflection. Okay. And then what's the concavity from 3 to 4.5? None. There isn't any concavity, right? If that, you can think about this like it looks linear, right? The derivative of something that's linear, the first derivative, right, of something that's linear is going to be its slope, and then the derivative of the slope is 0. And so there is no concavity there. Okay? So that's a lot of stuff that we are capable of evaluating on a simple graph of a function, right? Maybe this graph is not so simple, but I mean that's a lot of different like things we can analyze and evaluate and identify. Okay, or we want to be able to analyze, evaluate, and identify. Right. So questions on any of these pieces? Any of these pieces right here? Questions? All right. So that's what it looks like when you're looking at f. But now let's turn the page here, and let's consider this graph no longer to be f. Let's make the same graph a graph of f prime of x. So now let's call this the graph of f prime. So this is f prime of x here. Okay. And again, I know the numbers are not very easy to see, so if you want to rewrite them there. Okay. Okay, so again, this is the graph of f prime. Letter A asks, what are the values, or find the values of x for which f of x is not differentiable? Looking at our graph here, where does our derivative, where is the graph having problems? Where are the problems here for our graph? At what point? 2 and 3? Remember, this is the graph of f prime now. And we're asking where is f not differentiable? So in other words, f is not differentiable where f prime is not continuous. So is f prime not continuous at 2? I think it is continuous at 2, right? I see what you're saying though. F prime prime, so the second derivative would not exist here, right? The derivative of this function, f prime prime, would not exist here. But the function itself, f prime, if this is f prime, it's okay there. Where doesn't f prime work, or where is a problem with f prime? It's at 3. And since f prime is not continuous at 3, f is not differentiable at 3. Okay, so x equals 3 because f prime of x, okay, is not continuous at x equals 3. Okay, if you wanted to give further justification, you could say that the limit as x approaches 3 from the left of f prime does not equal the limit as x approaches 3 from the right of f prime. Okay, that would be a good justification there. Okay, since f is not differentiable at x equals 3, is f going to be continuous at x equals 3? We do not have enough information. Differentiability implies continuity, but something not being differentiable does not mean it's not continuous. Okay, what's our classic example for that? The classic example is the graph of the absolute value of x, right? the graph of the absolute value of x, right? It is continuous everywhere, right? No problems. Any x value you want to plug in, you'll get a y value, no problem. Right? But the derivative of this does not exist at 0. So be careful, right? We don't have enough information. Okay, we just don't have enough information. Okay, so again, differentiability implies continuity, and not continuous implies not differentiable, but we don't really have a rule for not differentiable. Okay, just because it's not differentiable doesn't mean it's not continuous. Okay, all right. So now we're supposed to find these three values here if possible. So we'll hold off on f of negative 2 for just now. Let's do the easy one. What is f prime of negative 2? According to our graph here. What is the value of f prime? Again, this is the graph of f prime. What is the value of f prime at the x coordinate negative 2? 1, right? So f prime of negative 2 equals 1. Okay, that's just obvious, just reading the graph, right? Negative 2, what's the y coordinate there? It's 1. Okay. Let's do the next easiest one, I'll say. What is the value of the second derivative of f at negative 2? Or in other words, what's the value of the derivative of this at negative 2? 0, right? It's going to be a horizontal tangent there. What is f of negative 2? Do we have enough information? No. Okay. Okay. We just don't have enough information there to be able to tell what happens to f. Again, this is the graph of f prime. We don't have quite enough information to determine that. Later, okay, we will be able to answer questions like that when we talk about integrals and things, but for right now, we just don't have enough information for that. Okay. All right. Find the interval or intervals in which f is increasing or decreasing. So again, we have to remember this is the graph of f prime. All right, we can go back to our little table here. Given the graph of f prime, if we want to figure out when f is increasing or decreasing, okay, a function f is increasing if the graph shown as f prime, the graph of f prime will be above 0, or the x-axis. So again, a function is increasing if the graph shown is f prime, the graph of f prime will be above 0. So we go here, we're looking at the graph of f prime. Where is f prime above 0? For what interval? From negative 3 to about 3.75 maybe? Okay. So, justify your answers because, what's our justification here?
F is greater than 0.
F prime is greater than 0 on this interval. Okay. So, if we're trying to then determine where f is decreasing, we're going to look at the graph of f prime, and we want to see when f prime is what? Less than 0 or negative, right? Okay, so we have two intervals for that. It's from negative 3.5 to negative 3. Sorry, negative 3.5 to negative 3. Union 3.75 to 4.5. Okay. Because, what's our justification here? F prime is less than 0 on these intervals. Okay. So that's just using, that's why we kind of made that little cheat sheet to refer back to, okay? A function is decreasing when, if the graph shown is f prime, the graph of f prime will be below 0 or the x-axis. So those intervals there where f prime is less than 0, f will be decreasing. All right. Find the intervals in which f of x is concave up or concave down. All right, so f is concave up. Well, let's take a look here. I think we just talked about that on the previous page. So, a function f is concave up when f prime prime is positive. If the graph shown is f prime, the graph of f prime will be increasing. The graph of f prime will be increasing. Okay, so f is concave up where this graph is increasing. All right, and we already kind of described those intervals earlier. This graph is increasing when it's starting at negative 3.5 up to 1. Union 2 to 3. Okay, because f prime is increasing on these intervals. As our justification. And so then likewise, f is concave down for, let's see, 1 to 2 and then 3 to 4.5. Because f prime is decreasing on these intervals. Okay. So there's our concavity. And finally, we use the graph of f prime here to find all relative extrema and all points of inflection of f. So let's identify relative extrema first. Okay, so relative extrema. A function f has a relative maximum when, if the graph shown is f prime, the graph of f prime crosses the x-axis. To the left, f prime is positive. To the right, f prime is negative. Okay? Do we cross the x-axis here? Does our graph of f prime cross the x-axis? Yes. Does it cross that we go from positive to negative? Yes, at that 3.75 right there. So f has a relative, what kind of relative extrema would that be? If we're changing, if f prime is changing from positive to negative, f will be changing from increasing to decreasing relative maximum. And again, we'll say that's about 3.75. Because f prime changes from positive to negative at that point. Do we have a relative minimum? So if f prime changing from positive to negative indicates a relative maximum, do we have a relative minimum there? Yeah, negative to positive at negative 3. And again, because f prime changes from negative to positive at that point. Please don't abbreviate. Well, or at least on tests and stuff like that, don't abbreviate. If you abbreviate on your notes, obviously I'm not going to be there to look at it and stuff like that. But please don't abbreviate on tests or quizzes. Use the full words. Okay, you can use f prime because that's referring to literally f prime, but don't use like neg. Don't use a minus sign and a plus sign. Do not use a minus sign and a plus sign on a test. I will not give you credit for that. Okay, don't do it because a minus sign means subtraction. A plus sign means addition. And on the AP test, you will not get credit for showing a minus sign and a plus sign. You need to write the words out, okay? Use your words, all right? Just like your mom and dad told you. All right, so example 3 here, I'm going to cut you guys loose on it and I want you to try this one, okay? Do it as you normally would, all right? So in other words, we just did this as what we want to eventually be able to do. This is what our ultimate goal is, to be able to do this on our own. Example 3, I want you to do it what you know how to do, right? Use the first derivative, use the second derivative, find all those points of information. Then we will look at how that relates to the information down here. Okay? So find those pieces of information for this graph. Okay? So go ahead and do that, and we'll see how far we can get from there. So, but go ahead and find those pieces of information. Yep. Oh my gosh, I didn't identify the points of inflection, did I, in the previous problem? Missed a wid. Okay, my bad there. Thank you for pointing that out there, Landry. Yes, okay, because it said find points of inflection too. Okay, so points of inflection, we go back to our little cheat sheet here. A function f of x is a point of inflection when if the graph shown as f prime, the point of inflection will be either a relative maximum or a relative minimum. So we can see there at, I'm going to call that 1. We'll say 0.5 there, and at 2 as well. Okay, so f has a point of inflection at x equals 0.5 and x equals 2 because, and now here the justification, we'll say this. F prime changes. So here's the key, right? Our justification needs to justify from the information that we are given. Since we're given the graph of f prime, our justification needs to be based on f prime. What is f prime telling us here? Well, we have a point of inflection because f prime is changing from from increasing to decreasing or decreasing to increasing. Okay, so I'm going to say because f prime changes from decreasing to increasing or vice versa at these points, and I think that is sufficient. Okay, you might want to add an additional sentence that says, since that's true, then f prime prime will be changing from negative to positive or positive to negative at these points, and therefore f will be changing from concave down to concave up or vice versa at those points. That's, a more complete explanation, but I think that's sufficient what we got right there. Okay. Anywho, so back to that, okay, we'll just work on this basically for the remainder of class, all right? How do you guys work on this one? We probably won't get done beyond that, okay? But I would like you to work on number 3 right here, okay? So we'll finish up this example 3 probably tomorrow because I don't want to push things here. So.